So let's just go back and look at charge of 1. So sodium chloride would have a charge of 1. Calcium hydroxide, the calcium has a charge of 2 plus, and the alum has a charge of 3 plus. So what you can see here is that assuming that the concentration is constant, what's going to happen is these are considered what we call indifferent electrolytes. So they only interact by compression of the double layer. So what you see is that sodium is less effective at compressing the double layer. Calcium would be more effective, and alum or the aluminum would be the most effective. So the aluminum would be the most effective coagulant. So hopefully that helps with that. And we can see that in this figure also. What you see here is we're plotting residual turbidity versus concentration. And if we just look at the 50% turbidity line, what you see here is that in order to achieve 50% removal of turbidity using sodium, we would need about 0.1, and this is molar concentrations. My toolbar hides the concentration. For calcium here, we're right in this range here. So we're talking about maybe 5 times 10 to the minus 3 molar. And then for aluminum, we're right in this range here, so maybe about 2 times 10 to the minus 4 molar. So you can see we need much less aluminum than we did calcium and then sodium. And if you remember, perhaps, that the critical coagulant concentration is a function of 1 over Z to the 6th. Okay, so that was the Schultz-Hardy rule, is what it's referred to as. And you can see that charge plays a very, very significant role on that critical coagulant concentration. And you can see that here. Now, this is Dodecal ammonium, and it behaves differently. Dodecal ammonium is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is Dodecal ammonium. It is a long chain, a carbon, so it's C12. This carbon chain here is hydrophobic. It does not want to be in solution. This, on the other hand, is a charged species, and it is hydrophilic and wants to be in the aqueous solution. So basically what happens is you form so if we have our charged particle, the ammonia end will associate with the negatively charged particle, so it will complex there, leaving these long chain species. And they tend to help ensure that the coagulant wants to precipitate, that wants to come out of solution. The problem is these hydrophobic ends tend to want to interact with each other, so if you add too much of it, then notice here you end up with a positively charged, and this is not to scale, but you end up with a positively charged particle. And what you see here is what we call charge reversal. So your negatively charged particle becomes a positively charged particle with these ammonium ends kind of sticking out of the particle. And those are in the solution, and that tends to, now you've got positively charged and your particles will repel again. Typically with these, where you have indifferent electrolytes, as I mentioned, that means that they're interacting by compression of the double layer. You can think of it that way. You typically don't get charge reversal, or you have to have very high concentrations. With aluminum, you'll see in some of the figures, you actually can get resolubilization at, depending on the dosage. So you can, it behaves, sodium behaves as an indifferent electrolyte, aluminum to lesser extent. Here, okay, you can ask the question, what we have is a freshwater river, and the question is, why do the particles of clay in a freshwater river settle as they mix with the saline water in the estuary? So why might that be the case? I'll give you a chance to think about that. So what's happening here?
So when it hits like the salt, does it just like coagulate?
Exactly. So you've got a high concentration of salt solution in the estuary, typically about 20,000 milligrams per liter, so about 20 grams per liter. So you're looking at molar concentrations of salt in that fresh water. So as the clay hits that fresh water, what you're doing is essentially adding sodium chloride, compress the double layer, and you get coagulation. So that's why in the image,
situation where if you hold it there,
in the image here, you see that the water becomes clearer. Okay, so what's happening is you're getting coagulation right in this region here. And those particles can flocculate, or if the water is quiescent enough, there's some mixing, so they mix, and then they settle out. And basically, this is the way a delta is formed in a river as that river hits the estuary. And I've just basically said what's on this slide. And you can see here, and we've talked about this. So this is the situation in the freshwater where the repulsive forces predominate and you have a stable colloidal suspension. And then when that fresh water hits the saline water, you get compression of the double layer and you form an unstable colloidal suspension. And we can use this in an engineering system to treat waters. Okay. I'm not going to talk a lot about Zeta Potential, but I want you to know that this exists. And basically, Zeta Potential is a way that we measure, what we do is we measure the movement of a charged particle in an electric field. So you take a water sample, you apply a charge, you measure the movement of that particle towards the pole of opposite charge. And based on that, you can then assess how effective the coagulant is. So you're really assessing and looking at that 0 point of charge. So where are you neutralizing the charged surface? So you can get a better sense of the mechanism, essentially, by which the coagulant is working. Now, we've talked predominantly about compression of the double layer. I mentioned adsorption and charge neutralization, which really is what happens with the Dodecal ammonium. Now, you can also get adsorption and what we call interparticle bridging, and that is shown here in this reaction right here. So basically, you can think about this as essentially your negatively charged colloid, and we have something like Dodecal ammonium, and what happens is these two hydrophobic ends interact and you form a larger particle as shown here. Now, the challenge with this is you have to be, these doses of these organic polymers are very, very sensitive, or coagulation is very, very sensitive to the dosage. You can, if you're not careful, you can see here we've got this particle, and it can essentially, the long chain bends, interacts with the particle, and you're not getting any interaction with another particle, and you simply just restabilize the particle. You can add too much of it, and you can see you've got all these other ends, and now you restabilize your particle, or you rupture, in this case you rupture the flock. So you form the flock here. It should settle, but in the flocculation system, if your mixing is too intense, you break apart the particles and now you restabilize it. So those are just some of the mechanisms that we have to be very careful of. So when we are operating a coagulation system, we talked about rapid mixing. So we want to ensure that the coagulant is dispersed throughout the solution. We then said that we have a flocculation basin. So we need to be very careful here, because if we have too intense mixing, we end up with this situation right here, where we actually rupture the particles and we restabilize the colloid. If we don't have sufficient mixing, then those particles don't come in contact with one another, so therefore they can't combine and become large enough. And tell it's Friday morning because the landscapers are here. I apologize. And then the last one is a meshment in a precipitate. So here we're actually adding so much coagulant that we exceed the solubility. And what we're actually doing is precipitating. So basically the flock that we're trying to remove, or the particles that we're trying to remove become enmeshed or encased within this particulate. So here we exceed the solubility. We're actually exceeding the solubility of the coagulant, and our particles that we're trying to remove become encased within that particle, within that precipitate. So in terms of coagulant properties, what we want from a coagulant is we want something that is non-toxic. Remember, we're looking at producing water that is palatable and potable. If we add a coagulant that's toxic, the water isn't going to be potable. We also want a coagulant that is relatively inexpensive. One of the problems with a lot of the organic polymers are they're very, very expensive. And so that increases the cost of producing water. We also want something that is relatively insoluble at neutral pH range. We don't want high concentrations of either calcium that's going to contribute to hardness, or aluminum in our treated water. Or in the case of where we add iron, we don't want high concentrations of iron in our water. You know the problem with that at MSU. And then typically we want a high charge density, and that was because of that Schultz-Hardy rule. So the aluminum is much more effective than calcium or sodium. Some of the common coagulants are listed here. These include alum. Alum, most common in the US is alum, ferric chloride, and now polyaluminum chloride, and you can see it here. It's a complex formula. It changes with manufacturer formulation, but these are typically the most common. And then where we add polyelectrolytes, these are most often added as a coagulant aid. So where we're trying to improve coagulation beyond what we can achieve with either one of these coagulants. One of the challenges of these coagulants is that they tend to be effective only in a fairly narrow range. So alum is typically most effective in a pH range from about 5.5 to 7.7. Ferric chloride is more effective at a higher pH, or more effective over a wider range, so it's from 5 to about 8.5. And then this polyaluminum chloride is effective over an even wider range. So you can see why polyaluminum chloride is now one of the most common coagulants used in drinking water systems, because it is so effective over such a wide pH range. These organic polymers, these include the Dodecal ammonium that I mentioned before. So you've got a long chain carbon molecule and then a charged end. And as I've mentioned, these are typically used, if they're going to be used, they'll be used as coagulant aids. They also may be used as filter aids, basically to try and improve the filtration, so achieving a more clarified solution, so you can actually get coagulation occurring in the filter. And sludge conditioning, where we're trying to improve the properties of the sludge so that that sludge dewaters more effectively. Because what we don't want to do with sludge is we don't want to be transporting a large quantity of water to the ultimate disposal site because of the cost of that. And this is just some of the typical organic polymers. They can be anionic, they can be non-ionic, they can be cationic. In flint, they actually added anionic and cationic polymers. They were having trouble achieving efficient settling after their lime soda ash softening process. So they actually, during the entire process in Flint that they were operating and treating Flint River water, they kept changing the concentrations of the anionic and cationic polymers. It's one of the few places where I have ever seen where anionic and cationic polymers are both added. But it was, as I've said multiple times when I talk about Flint, essentially what they did was they operated a pilot plant at about 15 to 20 million gallons per day, because they were struggling the entire time to maintain efficient operation.